Okay, March 8, 2022, this is the lab for physics 38 is electrical resistance. Okay, so what we're going to use, so remember your report for lab 1 and 2 are due now. You're going to learn about a very important electric and electronic device called the resistor. There are 4 important devices in electronic: resistor, capacitor, inductor, and transistor. I need you to download your spreadsheet from the shareable folder and rename it according to your group number. The lab is number 3. The equipment they are going to use is going to be, oh, let me show you. Oh, there's one more, right? That I didn't tell you. I gotta put in there. Here you go. The equipment that we are going to use is going to be one black cable with banana termination, a red cable with banana termination, what I have here in my hand is called a proto board. Okay, it's very cheap, this thing here. We can buy it almost in any electronic store. A proto board, that's the one that is missing here from my, I will leave my resistors at the end. Here we go. A digital multimeter, that's the digital multimeter we're gonna use. And 2 alligator clips. You might want to use also those little rubber stuff to insulate, rubber insulators for the alligator clips. And let's see, alligator clips and the resistors that's here in my 6 different resistors for, no, I have only 2 here. Let me show you how the resistors look like. I have enough resistors for 7 groups. 1, 2, 3, 4, 5, 6, 7. There's a total of 6 resistors. A resistor looks just like that. You're gonna be able to see it. I'm gonna just show you here in the recording, okay? This is a industrially manufactured device, but everything that we have around here in this room has an electrical resistance. Some have more electrical resistance than others. Metals, for instance, conductors has a very low resistance. This cable here has a very low resistance. But dielectric materials like wood, plastic, and glass, they have a very high resistance. What does it mean by high resistance? High and low resistance. High resistance means that the electric charges have a very hard time to move inside the material. Electric charges can move very easily inside a conductor material like this one, like this copper cable. But when it comes to dielectrics, electric charge don't move very well because these dielectric materials they don't conduct electricity as well as metals. Okay, that's the difference between them. So very high resistance, very low resistance. Okay, paper is a dielectric, right? Plastic is a dielectric. So those are all, they all have very high resistance. This material here also has a very high resistance, the plastic. But then there is some metals that are inside that we cannot see that has a very low resistance that allows you to perform experiments, okay? So the concepts are electric charge, electric force, electric field, electric potential energy, electric potential, electric current, and resistance. Okay? So there is a relationship between electrical resistance, electric potential, and electric current. There is a relationship between electric potential, electric current, and electric resistance. This relationship, very important. Relationship. This very important relationship. We're going to study that in more detail in our lectures. This very important relationship is called Ohm's law. And I'm going to emphasize that this is not a physical law, it's just a name put in between quotes. It applies only to a certain type of material. It applies only to ohmic materials. This so-called law, which is not a law, okay? This so-called law applies only to a special kind of material that we call ohmic materials. Your resistor is an ohmic material. Your cables here is also ohmic material, but then there are devices out there that are not ohmic, like diodes. Diodes are not ohmic materials on ohmic devices. The relationship that you have to know is the following. Let's see. Electric potential. Okay. Oh man, things. Electric potential is equal to resistance times current. Okay? Times electric current. You have to memorize that. Okay, so let's study this equation. Okay? Look, the higher the V, the higher the current, right? I'm going to rewrite this equation in a different way. It's better if you write it like that. We usually, have control over the electric potential because of batteries. We usually control the electric potential and the resistance. So it's better if you write this relationship in this way. The higher the voltage, which is related to energy, remember? Voltage is related to the energy of an electric charge. The higher the current. So the more energy that you give to an electric charge, the faster it is going to move. That's how you should look at that. And the higher the resistance of the material, the lower the current. Okay? The picture that you have to have of an electric charge. Let's see. I'm gonna give you a nice picture. Here you go. I have some P38. Here you go. The picture that you have to have for an electric charge is something like that. Okay. Okay, just to understand how electric charges move in a material, you have to think in terms of the atom and the electrons around it. Everybody understands that model, right, of the atom. This model of the atom helps you understand what happens inside a metal like copper, like this one, okay? So you have the positive charge here and the negative charge is circling the nucleus. The positive charge is 1800 times more massive than the electrons. Remember I told you that? They have the same charge, but their mass, the mass of the protons is 1800 times more. Has far more inertia than the electron. Okay, the positive charge and the neutrons too has far more inertia than the electrons. When you, okay, so some materials have what we call the valence electrons. The valence electrons are the ones that are on the outer shell of the atom, right? The further away you are in the atom from the nucleus of the atom, the electrons are the furthest, we call the valence electrons. And the further away you are, it's easier for you to extract that electron from the atom. Make sense? Right? And so if you're talking about a metal, what you have? You have a bunch of nuclei, right, inside the metal, on the order of the Avogadro number. and a bunch of electrons too. Many of the electrons are inner electrons. Most of the electrons are inner electrons. But the valence electrons that are on the outside of the atom, that are easier to extract, they behave in a very interesting way inside the metal. They don't stay bounded indefinitely to a single atom. Remember, that happens only to the valence electrons. They keep on jumping from one atom to another, but in a random fashion, okay? In a random fashion, unless you put an electric potential to the metal. Then the electrons tend to go in a single direction. Can you picture that? They add several atoms on the order of the Avogadro number. You have electrons jumping from one atom to another in a very random fashion, until you put an electric potential difference in the metal, and then all the electrons move in a single direction together. Okay, so here you go. Here I have my metal, my copper cable. I'm representing only the valence electrons. I'm not representing the inner electrons. And I apply a potential difference. Here you go. This guy here is a power supply. And what this positive side of the power supply is going to do is going to attract the negative electrons. The electron is going to tend to move from the left to the right here. It's going to pass this wire and move from the right to the left, combine with the positive plate of the battery. The chemicals in the battery has some potential energy that allows them to separate the negative from the positive, and the electrons then is free to continue moving in the circuit. Okay? Now, the battery was a battery. Battery is an engine capable of separating positive charges from negative charges. That's what a battery is. While your battery is working, it's doing exactly that. It's separating the negative from the positive, and it is adding potential energy to your negative charge. That's why the electrons can keep on flowing in this circuit. When the battery dies, all this flow stops because the battery can no longer separate the negative from the positive charge. Okay, that's the idea that you have to picture. Okay, here's a copper wire, valence electrons inside the copper wire, just the valence electrons, not the inner electrons. Remember, power supply, let's say 10 volts, and the electrons start moving. The electrons move to the right, but what you see here, oh, by the way, a very good picture. When you apply a power supply to this wire, what happens? It creates a uniform electric field in the wire. Can you picture that? Right now you should know what the electric field is, right? It creates a uniform electric field in the wire. It's possible to prove that mathematically. It's very difficult, it's a very difficult problem, but it is possible to prove. Okay? And this electric field is going to power those electrons. The electric field is to the left, the force is going to be to the right. Okay? And the electrons are going to move from the left to the right. Here you go. That's the picture that you must have. This speed is very small. It's on the order of centimeters per second. Okay? The electric current, what's the electric current? It's the number of electrons times its charge divided by the unit of time. Number of electrons that cross this gate here. Let's say picture that we have a gate here that keep on counting how many electrons pass through it. The number of electrons times the electric charge divided by the amount of time is the electric current. Okay? Here you go, the electrons moving. We're going to cover that in more detail in the lecture. Okay, here just want to have you. Now it is convention. There is a convention that has been around for a long time. Okay, even though the electrons are moving to the right, today's convention is that the current, the direction of the current, is opposite to the velocity of the electrons. Okay, electrons are moving to the right, current is to the left. Electrons are moving to the left, current is to the right. Why is that? There is a reason for that. Yeah.
I'm guessing it works better in practice.
What?
I'm guessing that it works better in practice for working with electronics.
Well, the reason is historical, okay? The reason is historic. When the science started to be studied, people thought that what carried the current was positive charges, not negative charges. Benjamin Franklin himself thought that the responsible for electric current was the positive charges, not the negative charges. Later on, we discovered it was otherwise. And the idea of electric current due to positive charges remain even today. Okay? Okay, so here you go. Oh, here you go. Copper wire is non-uniformities. All this junk here in your copper wire is responsible for the resistance in the material. Okay? So metals, materials in general, they're not uniform. They're not perfect. They have non-uniformities. Okay? So it's this non-uniformities plus the positive charges in the metal that affect the resistance of the material. Remember, the positive charges in the metal are attracting the electrons, right? But your battery is managing to pull the electrons away from the positive charge. So it is this non-uniformities plus the positive charges that are affecting the resistance of the material. Okay? So what you have to know, let me write that down here. At this point in time, you already know that the unit of voltage, of electric potential, right? Not voltage, but electric potential, that's the right name. The unit of electric potential is what? What's the unit of electric potential? Is the volt, right? You saw the definition of current. The definition of current, here you go, is delta Q over delta T. No, like that. Here we go. Delta T. That's the definition of electric current. Delta Q, the unit of delta Q over delta T is, we give it a name. This unit is so important, okay? That we give it a name. And there is more, you know. Some people prefer to use the current as a basic quantity, not the electric charge. Remember I told you that the electric charge is the basic quantity? In reality, some people prefer to say that the electric current, that's a basic quantity. And there's a reason for that. It's easier to measure an electric current than to measure an electric charge. Okay? So the unit of electric current is delta Q over delta T, which is also the definition of delta Q over unit of delta Q divided by unit of delta T, which is coulombs per second, and this coulombs per second, we give it a name, we call the ampere, and abbreviate by the letter A. Okay? So, the unit of resistance is going to be what? The unit of resistance, here we go, is going to be the unit of voltage, the unit of electric potential, divided by the unit of current. The unit of electric potential is the V, the unit of current is the ampere. This unit appears so frequently in physics that we give it a name. We call it the ohm, abbreviated by the capital omega. Okay? Abbreviated by the capital omega. You're going to see the capital omega in your multimeter on the lower right corner. Take a look there, the omega there. That's the scale we are going to use. The scale on the lower right. Omega. Okay? There are different scales in there. And what we are going to do, we are going to measure. We are going to measure the resistance of 6 different resistors separately and their combination. Okay? Let's take a look at the spreadsheet. I have the spreadsheet here. The first step is to measure the resistance of each resistor separately. I'm going to distribute that for you right now. Let's see. Is that the one? No, that's not the one I want. Must be this one here. Let's see. Oh no, only lab 2. Let's see. Let's see. I'm gonna display that for you. Let's see if I can find it. Download P38. Here you go. That's the one I want. Update Lab 3. Lab 3, right in here. See, that's the first table. See resistors 1, 2, 3, 4, 5, 6. That's the first table that you have to worry about. Okay, let me distribute. No, you know what? Come here. Oh, group 1. No, 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 not this one. Not this one. It's this one here. Group 1, come back, pick up your resistors. Make sure you have 6 resistors in there. Group 2, 6 resistors. Make sure you have 6. Don't lose those. Those are very small devices. Group 3, put it back. And by the way, notice that I have a little piece of paper there. Okay? Here you go. I want you to check it out. See, there's a little piece of paper. This paper is there for a reason. Okay? I want this piece of paper to lock the resistors in this side so I can close the envelope and the resistors are now secure and they don't fall. Okay? Did you get the idea? The resistors must be sandwiched between this paper and the front of the envelope. Okay? It's a way that I figured out to make sure that we don't lose the resistors. Yeah.
You can also use anti-static bags.
Yeah, that's those are resistors. They're very rugged. They don't get damaged. But some electronic devices, yeah, you have to use an electrostatic bag. But the resistors, no, the resistors okay. Resistors they're very rugged. It's not you don't have this problem from from like microcircuits and Arduinos, right? I have an Arduino here with me, by the way. Here you go, group 3. Group 4, make sure you have 4 resistors there. Group 5, group 6, and group 7. Group 7? Okay, since you mentioned electrostatic bag, right, here you go. Here's an electrostatic one. Okay, I have my microcontroller here inside, but that's not for this course, okay? That's what we call an Arduino. I'm going to start working with those things because I got a grant, and then I'm going to, I need to learn about Arduino, program it, and get my invention moving forward. Okay, so here you go. So we start with this one. Then I will tell you what to do next. Okay, then we have, that's the first part of the experiment. Measure the resistance of each resistor separately. And then what we're going to do, we are going to combine the resistors in series. I'll show you what does it mean. Measure their resistance and combine the resistors in parallel and measure their resistance. But let's concentrate on this one, okay? Let's concentrate on this one. I'm going to get one of those resistors. I'm going to show you how you're going to do, how you're going to measure their resistance. Here's my resistor. Here's my multimeter, right? Black with black, red with red. For a single resistor, you're not going to need the proto board, okay? For a single resistor, here you go. All you have to do is to clamp the ends of your resistor to measure its resistance. Make sure you use the most sensitive scale of your multimeter, okay? That's what you do. Do that and keep track. Keep track. You're going to measure the resistance in 2 different ways, okay? Here you go. That's the measurement using The multimeter. That's the measurement using the multimeter. Do this one first, that is easier, and then I'll tell you how to do this other one here, okay? Keep track of the other. Don't forget each resistor has a color code, okay? Keep track of those color codes as well. Let's start playing with that, and it's very important that you learn that stuff. It's going to be very helpful in real life.
Professor, are we using to keep the multimeter on?
What did you say?
Which setting did you say to keep the multimeter on?
Lower right.
Lower right.
Yeah, you gotta see which scale is the most sensitive one. Okay, you gotta test it. Which one is the most sensitive one? Okay, depending on the value of the resistor, you will be able to use only certain scales there, certain settings of the scale. Once you're done with that part, let me know. I'm gonna pause my recording and remind me to continue recording. There are two ways of measuring the resistance of a resistor. Okay, the oldest way of measuring is by color code. Okay, and but the simplest way, the easiest way to measure the resistance is by using the multimeter. What you're doing right now. Okay, in the past, it was very expensive to buy multimeters. So what they would put. Not everybody had multimeters. Not everybody could buy multimeters, right? So how they would tell you the value of the resistor? They would put a color code here in the resistor. Well, most resistors has like four bands, four color bands, but there are resistors that has a five and even six. Okay, this one here, how many we have? One, two, three, four, five. No, this one has five. Okay, yeah, it has five. But the resistor that we work with have only four. Each color represents a number for the resistor. Okay, and you have to learn how to read that. So you go ahead, the first band is one significant digit. Is the first significant digit. The second band is the second significant digit. When you are reading the resistor, when you are reading the value of the resistor by the color code, you're going to get only two significant digits here with four color bands. Okay? With five color bands, there will be three significant digits. So what's the rest? The rest is the multiplier, the power, 10 power, the power 10. Okay? 10 to the first, 10 to the zero, 10 to the second, 10 to the third. Okay? And again, each color represents a number, an integer number. And the last one is the tolerance of the resistor. The manufacturer, whenever they manufacture a resistor, he doesn't tell you that the resistor has exactly 1,000 ohms. They don't tell you that. It's impossible for someone to produce a resistor with an exact value of 1,000 ohms. So what they tell you? Okay, they tell you, look, your resistor is somewhere, is the value of the resistor is like 1,000 ohms plus or minus something, plus or minus a tolerance, plus or minus a percentage. Okay, so let's learn what this thing is all about, right? What those colors are all about. Here you go. If you go down there, Wikipedia, that's Wikipedia, okay? Each color has a number. Black is 0. See? Represents the number 0. Brown, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? If the number is in the third band, then you use this multiplier, 10 to the power 0, 10 to the power 1, 10 to the power 2, and so on. And then the tolerance. The tolerance is going to be, here you go, right in here, plus and minus 5%, plus and minus 2%. This one seems to be too much. 50% seems too much to me. but they have it, right? 25%, 10%, okay? 1%. Usually what you're going to see out there is going to be gold and silver. Oh yeah, here you go. Gold and silver. That are going to usually see out there. Oh, I'm sorry. It's not 50%. It's 0.5%. I'm sorry. Okay? So gold is 10%. Gold is 5%. Silver is plus or minus 10%. If there is no color code for the tolerance, so it's going to be 20%. And the others, here go, 1%, 2%, you know, 0.05%, and so on. Okay? So let's go to an example. We have this resistor here. First band is red. Red is which number? Red is number 2, right? So I'm going to write that down here. Okay, color code. Color code. Resistor has the following colors. Red, what's the next one? Red, violet, right? Violet, green, and gold, right? Green and gold. Yeah. So red, you go in your color in the table here. It's available in the internet. Okay. Color code. Look for color code, resistor color code. Red is 2. The other color is what? Violet. Violet is 7. The other one. Huh? Yeah. Yes.
27 mega ohm resistor
Yeah.
plus minus 5% tolerance.
That's right. It's already here, right? Here you go. 2, 7, followed by 5, 10 to the 5, right? I'm going to write that down here for you. 2, 2, 7 times 10 to the 5. Is that 20% or 10%? No, it's 5%. Plus and minus 5%. 5%, right? You put that. Remember, those values has only 2 sequence figures, right? Plus and minus. That's in ohms. So what you're going to do, okay, in my table, what you're going to do in my table, you're going to put just the number here, the tolerance. The tolerance here, or the upper value is going to be what? The value plus the percentage. The lower value is going to be the value plus the minus the percentage, okay? If it's 27,000 here, it's going to be 27,000 minus 5 plus 5% of 27,000. Here's going to be 27,000 minus 5% of 27,000. Okay? Make sure you preserve you have the right number of sequence figures there. So 2 ways of measuring. Let's write it down here. 2 ways of measuring. 2 different ways of measuring the resistance of a resistor using the DMM and using the color code. Okay? We're going to do both of them. We are going to use both methods in the first table for the first table. Okay? So go ahead, finish your color code there. You already should have already organized your resistors, right? And once you're done, yeah, Check the internet. You're better off checking the internet in your computer. You can, if you're having a problem reading the colors, you can always take a picture of your color code and zoom in, right, in your cell phone.
Professor, this resistor, the last color is like kind of erased off of it. I think it's gold, but
No, it looks more like brown to me. You take a picture on the right side.
yeah, the last color.
Oh, well, man. Are you talking about? Looks like it's this one.
Yeah, the one all the way on the.
Yeah, it looks like it's gold. Yeah, yeah. Okay, looks like it's
It can't be the first one because gold doesn't have
yeah.
a number.
Can be either gold or silver.
Yeah,
Take a picture of
no, I
that.
took a picture, but it doesn't show up clearly.
Yeah. Well, so you just have to guess.
I think
Yeah.
it's gold.
Okay.
Gold is more solid on there.
Okay. I will replace that another time. Hmm. Strange, huh? So what's going on here? Hmm. Interesting. Okay, and Nicholas, are you there, Nicholas? No, Nicholas. Harun, Musa, Athena, not here. Mario Jimenez. Okay. Dylan Martinez. Ramon Quintana. Toby. Pedro Flores. Kenny Villagomez. Robert Faust. Brian Inies. Abraham Perez. Lawrence Flores. Lawrence Flores, okay. Alexander Garcia. Patrick, not here. Patrick Vilavazov, nope. And Nolan Williams, not here either. Sung, there. Rafael Mercado. Ali, Genesis Bell, Jennifer Camarillo, and Alexis Negret. Okay. 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 19. Okay, save it. Plot the resistance DMM versus the nominal value versus the resistance for the color code. Okay, I'm gonna show you how what do we do. Here you go. Let me see here. Okay, what you have to do, you should plot this column here, I don't have the numbers there, versus this one, the middle one. Okay, that's what you're supposed to do. When you do that, when you do that, you are supposed to get a straight line with a slope equal to 1. Okay? If you get 0.95, that's fine. If you get 1.05, that's fine too. The problem is if you get 0.6 or 1.8, that's a problem. The multimeter value should be close to the color code value. Oh, wait a minute. I'm not. Let me go back here. Okay, so let's do that again. Here you go. Plot RDMM, right? Versus the resistance for the color code. And again, when you do that, you're supposed to get a straight line with slope equal to 1. Okay, the second table, right? What you're going to do next, we are going to combine two resistors in series. Let's start with resistor 1 and resistor 2. Okay? Combining those two resistors in series means what? Means to get one end of the resistor and touch at the other end of the other resistor. That's what means resistors in series. Simple enough? Okay? And then you measure the combined resistance. We call it the equivalent resistance. The multimeter goes at those two ends. When we combine resistors this way, the equivalent resistance is going to be R1 plus R2. Okay? R1 plus R2. There is a very simple way of, I don't want you to keep on holding those two resistors like that, okay? It's not good. It's not good practice to keep on holding your hand and then connect it here. There is a better way of doing that. The way to do that is to use the proto board. Okay? So I have an illustration here of the proto board of two resistors connected in series. Okay? You go ahead, plug one resistor on one of the holes, any of those, in the vertical, and plug the other one in this vertical line. Okay? Don't put it here, don't put it here, don't put it here. It has to be in this vertical line. This proto board was built in such a way that we have a wire connecting those holes here in this direction, another wire connecting these holes in this direction, and so on. So whenever you put those resistors in the same column, it's like they are touching each other. Okay? Make sense? So combine them in series, get your multimeter, right? Clamp here at this end, clamp here at the other end into the multimeter. That's how you do it. You're gonna do R1, R2, R1, R3, R1, R4, R1, R5. Make sense? Okay, so pause. So what's the third part? The third part, you're going to get your two resistors in parallel. Okay, here you go. Take a look at the PowerPoint. Here's resistors are in series. Oh, switch it. Resistors here are in series. Okay, resistors in parallel is going to be like that. Okay, you're going to connect. You know, how do you connect resistors in parallel? You connect resistors in series like that, right? That you already know. Parallel is just exactly what the name says. You connect the two ends of the resistors to each other. That's resistor in parallel. How do you do that in your proto board? Okay, just like the figure shows. You're going to put one end at one of the holes. The end of the other resistor is going to be in the same vertical column, right? You're going to connect the other end of resistor 1 at another hole, and resistor 2 at a hole of the same column. It's like that. Okay? That's how you connect your resistors in parallel. You are going to do R1, R2, R3, R4, R5, R6. Okay? So that's what you have to do. Yeah. No, doesn't matter. Any of those holes would work. Behind those resistors in series and parallel. We can prove that in the classroom. I'm gonna prove that for you in the classroom, okay? For resistors in series, you know, the equivalent resistance is the equivalent resistance is here you go for two resistors in series, right? For two resistors in series, R equivalent equal to R1 plus R2. Okay? That's what you're supposed to get. And that's what you're getting right now in your experiment. And what about for two resistors in parallel? For two resistors in parallel, the equation is, the equivalent resistance is what? Take a look. Here is R1 plus R2. Here is 1, is the inverse. Okay? It's very easy to memorize. The inverse, oops, oh gosh. The inverse is equal to the sum of the inverses. Okay? Can you remember that easily? Okay. So That what we have.